always experiments up to 3,000 psi. But probably an easier number is 1 MPa is 145 psi. Okay, Mr. What's your name? Ahad. You told me that it's 55. Is that right, Muhammad? Okay. Well, it's more or less 56 MPa. In geomechanics also we have a lot of uncertainty. So if you tell me the answer is 55.4328, I don't really care about that many decimals. As long as you get close to the answer, that's fine. Okay, so try to go through that and get the answer, and you should be close to that. So let's go to the next one. The next one is very similar, but now you have to do the multiplication point by point, okay? So again, there is a place offshore, and this is also an exercise to compute pore pressure with porosity. This table, somebody told me that there was an error. Actually, there is, but just let me copy the numerical values, okay? So it should be like this. This is going to be depth. Here we're going to have depth meters, bulk density in what do you think those units are? They look like kilograms per meter cube, okay? And here we have shale porosity. And this has no units, okay? Okay, the first thing here is to compute what is SV. We're going to do this in MPa. So, what can you see from this data? Where is the seafloor? Look at the density. Oh yeah. You see the change there? So there is a sudden change of density at that point. And also here you have the water depth is 500 meters, right? But you can also see over that here in the density. Okay, so if you want to compute SV, and in this case also it will be just pressure in this part, what is going to be the pressure on surface? On top of the water? Let's say 0, okay? 0 psi G, or 0 MPa. And then if you want to calculate what is going to be the pressure in the water at 100 meters, then we have to use what we just did before. It's going to be the density, but now because it's a variable density, I'm going to take an average of that density times G times the interval, and that interval is going to be this number minus that one, and that's going to give me stress, right? Density times G times depth, that gives me stress. That's a big number because those are pascals. So I'm going to multiply that times 1 to the exponent minus 6, so divided 1 million and I'm going to get the answer in MPa. 100 meters, 1 MPa. Remember that 1 kilometer or 1,000 meters is 10 MPa, so this will make sense. Okay, there is one more thing we have to do here. Because look, if I were to just drag this, I'm gonna get 1, 1, 1, 1, 1. There's something wrong here. What's the problem? Let's do it. Let's do it like this to make it even simpler. All these values are the weights of the layers for each independent layer, from 0 to 100, from 100 to 200. If I want to get the stress, which is an integral, which is a cumulative value, this one is going to be this value plus the previous one. And now, when I drag this, I'm going to get, what happened? Oh, not that one, that one. Okay? So, there you get the value, here it's 37. So now this is going to be SV, this is going to be MPa, and if I were to plot now, let me plot. Okay, just one sec. Usually depth, we like to see depth going down, and so I'm gonna. This is a plot of vertical stress as a function of depth. So we insert axis in here.
Do you mean access title?
What? Oh, what happened?
Are you trying to put in a title?
Yeah,
Yeah,
here.
yeah, it's that one.
Okay, so in this case, this is going to be SB in MPa, and this is going to be depth. Okay. Yes.
Can you show how you did the SP column?
Yes. So this formula is that number. So it's always the weight of the layer above times whatever was the value of the stress in the previous column.
Plus?
So you see, in this case, it's F5 plus G4. This one plus that and the previous value. So for example, if I were to go, this one is always the same. The weight of that times the previous value. So it's a cumulative summation of all these. Okay, so with that, you have the value of the total vertical stress, right? And then it tells you to compute what will be the hydrostatic pore pressure. And then later, and this way you will be able to do that. And later it tells you to compute what is going to be the pore pressure from shape porosity. So here, if you know the shape porosity, which is this value over here, you could tell what is the pore pressure. How? You know the value of porosity. From over here, you know what these two parameters are. Reference porosity and beta. And if you use this equation and the version that we saw in class, you will be able to get out of here what is pore pressure, because you know SV. So as a reminder, let me show you what question was that. Is this one, right? Let me try very quickly to see if I can make it work. So let's start from the bottom. This is going to be equal to, I know what is the value of SV, and this is going to be the natural logarithm of the porosity divided reference porosity. What is reference porosity? What is the value? 0.48, like that? 38? And all of that divided by beta. And what's beta? 0.03, and there you go. That should be the value of pore pressure. And I'm going to compute that only for the region in which there is shade, okay? No need to compute that for the other region where there is no shade. Now I can add another plot over here, and this is going to be the pore pressure. So this is the pore pressure, and this is the vertical stress. What would be more or less the pore pressure for the depth of 2 kilometers, considering hydrostatic pore pressure? You remember what was the hydrostatic gradient in metric units? MPa is 10 MPa per kilometer, so it will be 20. If we will be hydrostatic, you will be here 20. But clearly, here there is overpressure. Okay? At 1 kilometer, it will be about 10, so it appears that here there is no overpressure. Overpressure starts somewhere over here at 1,500 meters below the sea level. So, there are a few more things that you have to do in this problem, but it's not too difficult. Remember, the most important part is to get this equation right. How to calculate vertical stress whenever you have a density that varies with depth. Any question about this problem? Okay, let me go to the next one then, which is a little bit more difficult. Here,
Did you get that second one? Yeah, I'm just like working on the conversions.
you're going to have to download 2 files, okay? One is a well logging file, which is this file over here, LAS, and another file which is a deviation survey. And this is real data from a reservoir in Louisiana. And with those two, you have to do exactly the same as you did here, but the only difference is that you're going to have 1,000 columns or 1,000 rows to do that. So you cannot do this manually, you have to use a computer, okay? So, give me one more minute, guys. Let me show you how to get this file. So, you click in here, and then you go to undergrad homework. You go to homework number 2, and there you have these 2 files. These 2 files have this extension LAS and DEV that you won't be able to open it with any regular software, right? So what you would do is you download this, and when you download it, you just save it as a text file. And then from here, you will be able to, there are two things you can do. You can either copy this and paste it into Excel, or you can open it with MATLAB or with Python. I prefer if you go with MATLAB or Python. And we're not going to teach you Python, but we're going to help you if you need help with Python. I strongly recommend that you get to use Python, because coding skills are very appreciated now in the petroleum industry. Okay? All right, guys. I'll see you on Monday. Have a great weekend.